Good evening, everyone. Good evening, everyone. Welcome to all of you for today's ninth live interaction session on MATLAB-based programming lab in chemical engineering course conducted by Professor Parag Deshpande on NPTEL. My this is my short introduction. I am myself Prasil Kapadia. I have completed my BTech from SBNIT Surat in 2019. After that, I worked at Reliance Industries Limited at Jamnagar for a year, and there I mostly learned how to use SPEN software by direct application in industry. Then I completed my master's from IIT Kharagpur in 2022. There I learned a similar course of MATLAB from Professor Parag Deshpande. Currently, I am pursuing my PhD from IIT Bombay. So this is my web page and LinkedIn page, and this is the YouTube link where all the recorded sessions are uploaded. Before getting ahead with today's session, let's first discuss what we learned in last class. So in last class, we first took one example of initial value problem of CSTR in series. There was one reaction occurring A to B, and it was a first order reaction, and there were two CSTR in series. So we learned how to solve CSTR in series. Uh, we use some MATLAB inbuilt functions as well as numerical methods like RK4 method, RK2 method, Euler method. These all things we learned in last class. And after that, we started looking at boundary value problems. Some examples were we also learned kind of boundary problems like Dirichlet boundary condition, Newman boundary condition, Cauchy boundary condition, Robin mix boundary condition. These kind of boundary conditions we learned, and we found out what is the actual meaning of those boundary conditions. Then we also learned finite difference, forward difference, backward difference, and central difference. And we checked that central difference method gives really accurate predictions compared to forward and backward difference methods, because that order of error is less in case of central difference method compared to backward and forward difference method. So in today's session, we are going to solve boundary value problems, and for that we are going to use BBP4C MATLAB inbuilt solver. Let's first open the MATLAB and let's check about this MATLAB inbuilt function. So my MATLAB is getting open. Okay, so I will first open one live script. Okay, so what we are going to learn, we are going to use bvp4c command. Okay, so let's first take the problem statement. Consider the following boundary value problem solved using bvp4c solver in MATLAB. So equation is d square y by dx square plus dy by dx is equal to 2y. And we are given two boundary conditions, y of 0 is equal to 0 and y of 1 is equal to 1. So we are supposed to say how solution varies with respect to x. So here, why is it called boundary condition? Because value of this variable y is given at two extreme, and x is equal to 0 and x is equal to 1. Here we should note that there is no term related to time. Okay. So this is called boundary value problem. Before starting with this problem, let's try to first have a look at BVP4C MATLAB inbuilt solver. So I will be typing here BVP4C. So it will open out some screen. So let's first try to understand what is this BVP4C syntax. How are we supposed to use it? Okay, so this is we need to learn two things, BVP init and BVP4C. Let's first start with BVP init. What is BVP init? From form initial guess for boundary value problem solver. To solve this kind of equation, we need some initial guess. If you remember, we learned finite difference method. We see that we need value at I plus 1 location. If we are following central difference, we need value at I plus 1 location and I minus 1 location. So we need some initial guess, and this BVP init function, the use of this function is it forms initial guess for boundary value problem. So what is the syntax? So syntax is sol init is equal to BVP init x comma y. Okay. So let's take example. So if we read this, uses the initial x mass and initial solution guess y init to form an initial guess. So let's take this small example. So see, this is the problem. Y d square y by dx square is equal to minus y. And we are given two boundary condition y of 0 is equal to 0 and y of pi is equal to 0. So to use BVP init, this is the function of, sorry, where did it go? Yeah, here BVP init x solution is equal to, this is not actually solution, but sol init is equal to BVP init x mass. So we are creating a mass. So here our limit was from x is equal to 0 to x is equal to pi. So here in this example problem, what is done between x and 10, x and pi, 10 equally spaced mass points are created in this xmass linspace command that is stored in xmass variable. And what we need x comma initial guess. So for initial guess, here they have written one separate function, but we can avoid that. So this is how bvp init function or bvp init MATLAB tool work, inbuilt tool work. Now let's check about bvp force. So this is the command actually to solve uh, ordinary to solve this boundary value problem. So the syntax of this command is we need to give ODE function. ODE function meaning the function where we are describing our equation. So ODE equation. Then next one is boundary function, BC function, where that stands for we are supposed to give boundary conditions. And sol init meaning that x mass, the size of mass, and initial guess. So these things we need to give in this kind of problem. So first let's try to understand this problem. So let's try to do it here first, and then we will write the code. The problem is d square y by dx square plus y is equal to 0. And here it is given that y is equal to 0 at x is equal to 0 and y is equal to 2 at x is equal to pi by 2. Sorry. Yeah, here. I'm sorry. Yeah, x is equal to pi by 2, y is equal to 2. So what are we going to do? We are going to write that we will be using only two variables. So we will be converting, we will be representing our equation as a system of first order equations. Okay, so how do we convert it into first order equations? We first assume that y is stored in y1. Okay, the value of y is stored in in y1 variable. So and y2 is stored in y prime is stored in y2 variable. Correct? So if my y1 is y, then my y1 prime will be y2, and my y2 prime, what is what is y2 prime? Y2 prime is nothing but minus y, that is minus y1. So what do we need to do? Whenever there is the term of d square y by dx square, we need to replace it with y2, and all other single derivative and other terms we need to replace it with single y1. Okay, so see here they have written the function first. So the first equation, okay, we need to split this equation. So d square y by dx square is a first term. So that is represented by y of 2. And my second term is minus y. So minus y is represented by y1. So minus of y1. So this is how we are supposed to define our function. Now we also need to give boundary conditions. So boundary conditions are given as y of 0 is equal to 0 and y of pi by 2 is equal to 2. So we can write our boundary condition as y of 0 is equal to 0 and y of pi by 2 minus 2 is equal to 0. Correct? So boundary condition, one boundary condition is given as y(a) of 1, and second one is given ybb is meaning yb meaning at another end, final end. So yb of 1 minus 2 equal to 0, we don't need to write. So our first boundary condition is ya of 1 and second boundary condition is yb of 1 minus 2. So this is for boundary conditions. And initial guess, we actually don't need to mention it like this. I will show you how we can just simply do it. Okay, so let's try to write down a code for this. The question is d square y by dx square plus y is equal to 0. So I will first do clear all CLC. So I'll be writing down my equation d2y or y prime, y double prime plus y is equal to 0. This is our equation. So what do we need to do? We need to write y1 is equal to y and y2 is equal to y prime. Okay. So first, if we want to write this line, okay, let's understand step by step. First, we need to define our initial this command sol init, meaning this bvp init function we need to use. So for that we need mesh size and some initial guess. So let's say I am giving x mesh size from 0 to pi by 2, right? 0 to pi by 2. Let's say I am giving my x mesh is equal to linspace command. I hope you remember what is linspace. It creates between a and b equal interval of points that we have given. So one is 0 and another is pi. Okay, let's see here. If I write pi, it will give me directly value. So we don't need to write 3.1416 pi by 2. And how many points we need? Let's say we need 10 points. Okay, so we have created our mesh. Now we need to use bvp init function. So I will write sol the way they are writing in the example. I'm not doing anything new. The sol init is equal to bvp init c form initial guess for boundary value problem. So bvp init, first I need to define my x, and the second thing that I need is x guess. So let's say I am giving some guess value as 0, 1. I don't know. So I'm just giving this random value. We need two values because it's a boundary value problem. Okay, so these we have defined. I hope till now it is clear. So next what we need to do? We need to, for using BVP4C MATLAB inbuilt function, we need to write these two functions, ODE function and boundary condition function. So let's write it down, ODE function. So let's say function, I will always define it as dy dx is equal to, let's say I'm writing ODE fun, ODE function. What are my variables x comma y? So when I start function, I need to end function. So my equation is dy dx is equal to y double prime. So y double prime, I will be showing it via y2 of 1, and my second is y double prime. Okay, how can I write it here? Let me add one more comment. I can write it here as y double prime is equal to minus y. So my second comment will be minus of y1 of 1. Not y1, sorry, it's just y of 1 because we are already writing here 1 and 2. So here it will be y of 2 and y of 1. And I just need to end the function. I guess it is already done. Okay, so this is how you can write down your function. Okay, now we also need to write down a function for our our boundary condition. So function, what should I say? Let's say I'm saying m is equal to boundary condition. What are they calling? BCFN. BCFUN means boundary condition function ya and yb. Okay, So here, let's say my m is equal to, what is my first boundary condition in this problem? Y of 0 is equal to 0 and y of pi by 2 is equal to 2. Okay. So we are told two extreme ends. So y of 0 is equal to 0. So ya of 1 minus 0 is equal to 0. So I'm just writing y of 1. And my second boundary condition is yb of 1 minus yb of 1 minus pi by y of yb of 1 minus 2. Correct? See here, yb of 1 minus 2. It will automatically understand that it is at x is equal to pi by 2. Okay. So here um, we have given this boundary conditions. Correct? So now to solve this equation, let's say I'm writing whatever they are following. Let's do that only. Let me close this tab. It's not required. Yes. So for this, what are they calling it? So see, sol is equal to solution is equal to it. Solution is equal to this thing, bvp4c, bvp4c. So see, solve the boundary value problem fourth order method. And when I use bvp5c, so it uses fifth order method. I don't know why it's not coming out. See, fifth order problem, fifth order method. Okay, so we are going to currently use bvp4c. So first I need to define my ordinary this differential equation. So I will call that function by ODE FUN, the name of the function. I will put one comma, correct? And then I will add the boundary condition. So that is represented by boundary condition function. BCFUN, comma. What do I need to give? I need to give this containing this x mass and 0, 1. So this is what I need to do. So let's try to run this, but it is showing some kind of error. Okay, I am having two ends. These I need to close. So okay, let me run this. So see, I have solution, but in solution, from this I need this first row and all columns. This is my solution. Okay, first row and all columns. So what can I do? Let's say I'm plotting my solution. So X mass I am already having. Let's say my Y underscore, or let's say just Y is equal to sol. So how do I write it? Sol dot, what is the name here? Y. Sol dot Y. What is the solution? First row and all columns. This is my solution. Okay. And what is my X? X is equal to sol dot X. Similarly, sol dot X. We don't need to mention first row, second row, because it's just sol dot X. Okay. So we have X comma Y. So what we can do, we can now plot our solution. So we can use plot X comma Y. Let's say I'm using this dots. Okay. And let me run it. So see, if we verify our problem, so what is told? When x is equal to 0, what was our boundary condition? X is equal to 0, y is equal to 0. And when x is equal to pi by 2, that is at 1.57, my y is equal to 2. So see, our solution is matching. So what further we can do? We can increase our mesh size. Instead of 20 points, let's say I'm creating 100 points. So the curve will be smoother. See, this is how it looks. So let's say I'm giving some X label, Y label things. So let's say X label is X. And let's say Y label is Y. Okay, here I want to give line width of let's say 1.5. To see how beautiful it's looking. Let's say I just want a line. See, this is our solution. Okay, so this is how we can solve boundary value problem. Let's take one more example from this example file. Examples given in MATLAB. So this is the equation. Let's try to solve this. This looks a bit complicated than this one. So we will write code from initial. We will not copy this. So let me just save this code. This is our ninth week, right? In nine. I will write example underscore one. Okay. So this is the first question. Let's try to solve the second problem. We will not copy paste from here. We will be writing down our own code. So I will write clear all CLC. Okay, so let me first copy the problem statement. Okay, let me do one thing here just for my understanding. Boundary condition is given as y of 0 is equal to 0 and y of pi by 2 is equal to 2. Okay, so let's write it down. So our equation is y double prime plus 2y prime by x, y double prime. Okay, let me add comment. Y double prime plus 2 y prime divided by x plus y divided by x raised to 4 is equal to 0 plus y divided by x to the power 4 is equal to 0. This is our this is our equation. Let's write down boundary condition. Y of 1 divided by 3 pi is equal to 0. Y of 1 divided by 3 into pi is equal to 0. And my second boundary condition is y of 1 is equal to sine of 1. Okay, y of 1 is equal to sine of 1. Okay, so what we need to write down, y1 is equal to y, y2 is equal to y prime. So our actual equation is this thing. Let me just copy this equation. Is equal to negative and negative. Correct. So let's first define our mass. So x mass is equal to lean space between 1 divided by 3 pi and 1 divided by 3 pi and 1. So my first one is x1 divided by 3. Please be careful while writing this. 1 divided by 3 into pi. Okay, this is my first, and second one is x1 and my x2 is 1. Let's say I want to create 10 points. So I have defined my x. Now I will use what is the thing? Let's follow the tradition of writing sol init, sol init is equal to bvp init to form this boundary value problem, xmas, comma, initial guess. Let's say our initial guess, we can give something 1, comma 2. Okay, this is our initial guess. So let's first write down this thing, that solution is equal to bvp 4c of at the rate. First, we need to write down ODE function where we are defining our equation. Then second is boundary condition function at the rate BCFUN, comma, this sol init. Oh, no, I don't want to click on that sol init. Yeah. So this is done. Okay, so let's first write down function. Let's say dy dx is equal to what is the name of the function? ODE fun x comma y, correct? And let's put and so dy dx is equal to what is our equation? First term is y double prime, so that is represented by y of 2, and my second term is minus 2 into y of 1, 2 into y of 1 divided by x. Okay, this is our first term. So let's put one more bracket, minus y of, let's again here put one bracket, y of 1 divided by x raised to 4. Okay, so we have defined our function equation. Now we need to define boundary conditions. So let's say function m is equal to BCFUN. We need ya, comma, yb, correct? And so let's define boundary condition. M is equal to, okay, what is my first boundary condition? Ya, y of 1 divided by 3 pi is equal to 0, meaning ya of 1 is equal to 0. So my first boundary condition is ya of 1 is equal to 0. So ya of 1 minus 0 is equal to 0. So that is nothing but ya of 1. And my second boundary condition is my second boundary, sorry, my second boundary condition is y of 1 is equal to sine of 1. So yb of 1 minus sine of 1 is equal to 0. So yb of 1 minus sine of 1 is equal to 0. So here I have defined my boundary conditions. So now let's say I want to define my x. So I am just rewriting it. X is equal to sol dot x file is x, and my y is equal to sol dot y first row and all columns. It will be my y. So we will be plotting it. Plot x comma y comma, let's say this is just a line with line width of 1.5. It's plot, not ploy, plot. So x label, let's say it is x, and y label, let's say it is nothing but y. So guys, one thing to take care of here. So as it is y is equal to 1, so we are writing y of 1, but let's say we were given that dy by dx is equal to 5. So we will be writing y of 2, because my y of 2 will be dy by dx. Okay, so take care of that. Let's run this and see what we are getting. So see this kind of weird solution that we are getting if we match it with, if they have given it. Yeah, it is something weird starting from 0.1. So there is one line for BVP4C. This is true solution. If you see this example, this is true solution is represented by a line. Circles are my BVP5C and stars are my BVP4C. So you can see that BVP5C is doing really well. So if we do BVP5C, we will not see huge amount of change here. So this is the solution that we are getting at using BVP5C. So what is sine of 1? It is 0.84. So it is coming out near somewhere 0.84. Okay. So let me save this example. E9. This is example 2. I guess it's not saved. No, it has just saved data. I don't want data. I want everything. So let's say Control S. Why is it automatically saving there? I don't know. Sessions. Example underscore 2. Let's say I want to. .m. I don't want to save it in. Yeah, it is saved like this. Okay, so we have already now learned how we can use this BVP 4C and 5C. Okay, so now let's try to take the problems that we have left in last assignment. So this is the problem statement: d square y by dx square plus dy by dx is equal to 2y. And we are given that y of 0 is equal to 0 and y of 1 is equal to 1. So let's try to solve this problem first and try to answer the question. So first, clear all CLC. Okay. So my equation is, we don't need this thing right now. So our equation is d square y by dx square. So I will write down y double prime plus dy by dx, that is y prime, is equal to 2 into y. So I can write down my equation as y double prime is equal to minus y prime minus 2y. Okay. Let's add boundary conditions. Y of 0 is equal to 0 and another one is y of 1 is equal to 1. So what we are supposed to do? Y1 is equal to y. How do we write it? Y1 is equal to y, or instead of y1 you can also write it as y of 1, but it's just understanding. Y1 is equal to 1 and y2, y1 is equal to y and y2 is equal to y prime. Correct? So let's try to solve this problem. So what do we need first? We need mesh size. Correct? So let's say my x mesh is equal to lean space of 0, 1. Let's say I'm just putting 5 points. So 0, 1, 5 points. My x mesh is created. And my next term is solve init. is equal to bvp init. First, I need to write my x mass. Then I need to write down my initial guess. So let's say my initial guess is 0, 1. Okay. And let's say my solution is equal to bvp 4c of, I will be defining my function showing equation using ODE fun. Then my boundary conditions using BC fun and my this solve init. Okay. And my x will be sol dot x and my y will be sol dot y, first row all columns, and I will be plotting it. Let's do it first, then write down the function plot x comma y comma, let's say I am putting these squares, okay, with let's say x label is nothing but value of x and my y label is nothing but value of y. Okay, so let's now try to write down the function. So function dy dx is equal to ODE function x comma y. I will put one end because if I start the function, I need to end the function. Okay, so my function dy dx is equal to, let's write down the first equation. My first equation will be always y of 2. And my second equation, what is my second equation? Minus y of 1 minus 2 into y of 1. Guys, just a minute. I guess I have made some mistake. Okay, guys, we have made one small mistake, not here. Yeah, here we have made a small mistake. Here it should be y of 2. Yes, minus 2 into. Okay, let me just check it once again. We have made a mistake because y1 prime. Y1 prime is y of 2. So we need to write it as y of 2. So that is a small mistake that we did. See, minus 2 into y of 2 divided by x. Okay, so this was our small mistake. Yeah. So here, so my second part will be, yeah, here it should be plus. Yeah. Minus y prime means minus y of 2. Sorry, here it's plus. Yeah. So here it should be y of 2 minus is 2y minus y of 2. Sorry. So 2 into y of 1 minus y of 2. Okay. So this is my dy by dx. Now we need to define boundary conditions. So function m is equal to bc function ya comma yb. Whatever I start, I need to end. So m is equal to, okay, what are my boundary condition? Y of 0 is equal to 0. So ya of 1 minus 0 is equal to 0. So y of 1. And my second boundary condition is y of 1 minus 1 is equal to 0. So yb of 1 minus 1. So this is my second boundary condition. So I guess I am set with the problem. So let me run this. So see, I am getting this kind of solution. What is asked in the problem? The solution plot exhibits that y varies. So directly at as is the square root of x. inversely as square root of x, directly as x, inversely as x. So you can see that when x is equal to zero point 0.2, it's 0.2, this point, so it is equal. 1, 1, so it is directly varying with x. So our answer will be option C, directly as x. So if I increase my this points, instead of 5, let's say I'm doing 10, it's not going to change the nature, obviously. If I do 100, if you see there is a slight, very slight curvature somewhere in between. If I see the solution, okay, it's not exactly varying with x. It's not exactly directly varying with x. There is bit discrepancy. It's not exactly x. So see, if you see this 0.01, x is equal to 0.0101, it is 0.0117. So it's not exactly as x. You can also see it's not a completely straight line, but it is directly varying with value of x. So our correct answer will be option number C, directly as x. I hope this point is clear, where we have learned how to use BVP4C solver. So let's take one more example. The energy balance equation for a heat generating fluid flowing in plug flow through an insulated pipe of length L is given by 1 of Prandtl number d squared theta divided by d gamma square, plus Reynolds number into d theta by d gamma plus q into theta is equal to 0, where theta is given as t minus TL divided by T0 minus TL. So it is non-dimensionalized form, and gamma is given as 1 minus x divided by L. The coordinate x is the direction along the axis of the pipe. So it is varying with axis of the pipe, and the temperature T is a function of x only. T0 and TL are the temperatures at the inlet and outlet of the pipe respectively. So T0 is the temperature at inlet and TL is the temperature at the outlet. The term Q is related to the heat generation, whereas Reynolds number and Prandtl number are Reynolds and Prandtl numbers. Yeah. The boundary conditions are theta of 0, theta at gamma is equal to 0 is 0, and theta at gamma is equal to 1 is 1. So when my t is equal to TL, my theta will be equal to 0, and my t is equal to T0, my theta will be equal to 1. Considering these values, Prandtl number is equal to 0.002, Reynolds number is equal to 10 raised to 4, and Q is equal to 5 into 10 raised to minus 3 theta. The system is solved using BVP4C solver in MATLAB. From the plot of theta versus gamma, it is found that theta attains a steady state at what value of gamma. So we are supposed to first find the solution. And we are supposed to say at what value we are getting steady state. So let me first just save this problem. Okay, so let's take this next problem. Okay, let's take this problem and let's try to solve this. This one is really easy problem. It's the same problem, but the only thing is the equation given is in somewhat complicated. So let's write down clear all CLC. So let's first write down the equation really carefully. So our equation is, let me close this. So our equation is 1 divided d squared theta by d gamma square Prandtl number. So y double prime divided by Prandtl number plus Reynolds number into y prime plus q. Okay, it's in theta form, so but I can't write theta, so I will just write y. Q into y is equal to 0. So my equation will be y double prime is equal to this term. So first negative of this term, and this whole term is multiplied with Prandtl number. Okay, so this is my equation 1 y double prime, and this is my equation 2. Okay, now let's write down boundary conditions. The boundary condition is given as theta at gamma is equal to 0 is 0. So I will write y of 0 is equal to 0 and y of 1, I guess 1. Sorry, y of 1 is equal to 1. Same. Okay, so let me just write down one thing here. Y is equal to theta and x is equal to gamma. It's just for my future reference. Okay, so let's first create the mass size. So it is between 0 to 1. So we are just supposed to say when we are achieving steady state, so that we can directly say from looking at graph. When do we get steady state? When the value is not changing. So that is steady state. So x mass is equal to Lie space of what are my boundary conditions? Boundaries 0, 1 are my boundaries. So 0, 1, let's say I'm just creating 10 points. Okay. So this is my size of mass x. Then my sol init, similar thing. I'm not doing anything new here. This is just syntax is equal to bvp init x mass, comma x mass, comma initial gas. Let's say it is some 0, 1. And we will be writing solution is equal to bvp. We are supposed to bvp 4c or 5c? bvp 5c. So bvp 5c. Let's say my name of the function is ODE function. Then my boundary condition is BC function. And my initial, not initial gas, this sol init thing. Okay, so I have given my solution. So here also my x will be equal to sol.x. So let's say here writing instead of x, I am writing gamma. Guys, just a minute. I'm just checking something. Okay. So let's say I'm just writing gamma. Or let's just write x is equal to sol.x and my y is equal to sol.y, first row, all columns. Okay. This is my x comma y. So if I will plot x comma y comma, let's say this symbol with line width of let's say 1.5. Yeah, my x label. What is my x label? My x label is gamma. And what is my y label? My y label is theta. Okay, so we need to now write down the function. So my function is function dy dx is equal to function dy dx is equal to ODE function ODE fun x comma y. So this is my ordinary differential equations function. My equation is dy dx is equal to, my first equation is nothing but just y of 2 It will always be y of 2. You don't even need to think. And my second equation is this, minus Prandtl number minus Prandtl number into this term is common, Reynolds number into y prime. So I will put one more bracket, Reynolds number into y prime means y of 2. Yeah. Then what is next? 2 plus q into y plus q into y of 1. Okay, so this is my equation. But now here we need to define all these things. So what is my Prandtl number? My Prandtl number is equal to, what is it given? My Prandtl number is equal to 0.002. 0.002. This is my nothing but Prandtl number. Then next part is Reynolds number. My Reynolds number is equal to 10 is to 4. So 1, 1, 2, 3, 4. Or I can just write 1e4. So it will take 10 is to 4. And my q, so see here, there is a catch. Q is equal to 5 into 10 is to minus 3 into theta. So 5e minus 3 into theta. What is theta? Theta meaning y of 1 into y of 1. So this is my q. So this we have written down our equations. So let's try to write down the uh, function for this boundary condition. So let's say function m is equal to bc fun ya comma yb. So it's the same boundary condition, I guess, like from previous problem. M is equal to, what is it given? Y of 0 is equal to 0, y of 1 is equal to 1. So my boundary condition first is y of 0 is equal to 0. So ya of first value and yb of 1 minus 1. Okay. So this our problem statement is ready. So let's try to run this. So see, we are getting it. So when are we achieving steady state? We are achieving it near this. After this point, it's not changing. So let's say at x is equal to 0.2, it's at steady state. So my answer will be x is equal to 0.2. Correct? So let's see one thing. Here I have written gamma and theta, but these are not, this is not what I want to say. I want to show it as a symbol in plot. So how can I do it? I just need to put one backslash, gamma and theta. And let's say I'm running it. So see, it is showing me as gamma and theta. Okay. So wait, let me first save these and let's try to. So if we see here, dot slash gamma, I'm just typing it and I want to see what I'm getting. Not this thing. These are showing mathematical function. I don't want to see mathematical function. This is beta function, but I don't want it like this. Let's say I'm writing it here beta. So it is showing me the symbol of beta. Let's see if I'm writing alpha. It will be showing me the symbol of alpha. Similarly, if I write delta, okay, but these are all small letters. But let's see if I want a capital letter. I don't know if this will work or not. I'm just trying it. I want capital delta means bigger delta. Yeah. So if write it down, if I start with capital D, then it will show me. If I write here capital theta, so it will show me big uppercase letter of theta. So see, it is showing me uppercase. So this is how you can do it. So our initial thing was theta and gamma. Okay, how capital gamma looks. See, this is my capital gamma. So this is how you can do this thing. So till now, what we have learned how we can use BVP 4C and BVP 5C functions. Okay, let's say I want to do one more exercise here. X is actually not going to change, but let's do it like that only. Let's say I'm writing my second solution using BVP 4C. Okay, I just want to compare how we are getting it. Okay. X1, X2 are not going to change. It is the same thing. Okay. So here I will be plotting two in one. So I will need to hold the plot, hold on function, hold on command, not function. X2, comma, Y2. I will need legends here. I have not added, but those two are both are identical actually. I will add here legend. First one is BVP 5C and my second one is BVP 4C. If we will reduce the point, I guess then we will be able to differentiate. Right now, both are coinciding with each other. If I open it in a big screen, where did that plot go? Yeah, here. Okay, so here it is really difficult to differentiate. So let's do one thing. Let's just take very few points instead of 10. Let's say I'm just taking 5 points. It may or it may not give. So see, some points are different. It's 5, right? Why is it showing 50? So see, here there are some changes and here there are some changes. But why is it showing like this? I have just why is it showing 20 points? Okay, so this is how we can learn this. Just give me a minute of break. Okay, so let's move ahead. Let's move ahead with another problems. Of those problems, those are directly related with chemical engineering. And this was one, but let's take one more problem. Let's first try to read down the problem statement carefully. The problem statement says that consider a one-dimensional heated rod in which the heat transfer takes place by both conduction and convection. So there is a rod, and from that rod, heat transfer is occurring via both conduction as well as convection. Governing equation can be derived as the one given below: d square t by dt dx square plus h into t infinity minus t is equal to 0. So this is the governing equation, where the ambient temperature and the heat transfer coefficient have been denoted as T infinite and H respectively. So T infinite is my ambient air temperature and H is my heat transfer coefficient. The boundary conditions are T of 0 is equal to 300, means at X is equal to 0, my temperature is 300, and T of 10 is equal to 1000 Kelvin. So two boundaries at which we are given these conditions. The length of the heated rod is 10 meters. So this, if even if they don't mention, we should understand it from here. So the heat length of the heated rod is 10 meter, and the convective heat transfer coefficient H is equal to 0.05. We are given the value of H, and every unit is in SI unit, 0.05 watt per meter square per Kelvin. The ambient temperature is T infinite is equal to 298 Kelvin. So this is the pictorial form of the problem statement, where this is the rod, this is conduction, this is convection. So X is equal to 0. I have some T is equal to 300 Kelvin, and my X is equal to L. At X is equal to 10, my temperature is 1000 Kelvin. For the system with the specifications given above, the first part that we need to do is determine the temperature profile along the length of the rod as a function of ambient temperature in the range of 100 to 500 Kelvin, with other specifications remaining same. So we need to find temperature profile where we are given H is equal to 0.05, and we are said that vary the T infinite from 100 to 500 Kelvin. So let's first write down the simple code and let's try to solve it with T infinite is equal to 298 Kelvin. Let's see what we are getting. Okay. So I will write down clear all CLC. So my equation is d square t by dx square. So t double prime. Okay, let me do just one thing. Yeah. So my equation is d square t by dx square plus h into t underscore infinity minus t is equal to 0. So this is the equation that is given to us. Okay. So how can I write down this equation? I can write down as this t double prime is equal to minus of this whole term. Okay. So we are given boundary condition. T of 0 is equal to 300. T of 0 is equal to 300, and T of 10, that is the length of the rod, is equal to 1000. So these are our boundary conditions. So what I will do, I will write y1 is equal to t and y2 is equal to t prime. Okay, so let's first write down our simple equation. X mass is equal to lean space. Let's say 0 to 10. We are taking some 10 points, and sol init is equal to bvp init x mass comma initial guess. Let's say its boundary condition is initial guess. Okay. Now my solution will be equal to bvp4c at the rate ODE function, comma at the rate boundary condition function, comma. So this is my solution. So my x will be equal to sol dot x, and my y will be equal to sol dot y first row all columns. And if I want to plot this, so I will use plot function. On x-axis it is x, on y-axis it is temperature. Sorry, here I will be writing y. Then let's say I just want a line with let's say I want it with green color. Okay, let red color. Let's say it's red color. Then I want line width to be 1.5. And my x label will be temperature in Kelvin. Let's say my y label will be, sorry, my x label will be not temperature. This is my y label. And my x label will be length. And the unit of length is given as meter. Correct? So let's say I'm giving one title, temperature variation along length of the rod. Okay. So let's first write down our function now. Function dy dx is equal to ODE fun x comma y. So my dy dx is equal to, first will be always y of 2, and my second term will be minus h into t infinity minus t. So minus h into t underscore infinity minus tt, meaning y of 1. Okay, so this is my equation. So here I need to specify what is my h and t. So my h is equal to, I guess it is given as 0.05. 0.05, and my t infinite, t underscore infinity is equal to 298 Kelvin. Okay, so what we have done, we have defined our equation. Now let's write down function m is equal to boundary condition function ya comma yb. Correct? My m will be equal to, okay, what is my first boundary condition? T of 0 is equal to 300. So ya of 1 minus 300, and my second T of 10 is equal to 1000. So yb of 1 minus 1000. Okay, so these are my boundary condition. I will put one and here. And let's try to plot this. Okay, I have given somewhere. Okay, it is being some error. Let's do it now.
Maybe
It
you have
should
to
to
say what's the y of 1 or something.
sorry.
Y. So y has two vectors, right? Two columns.
Yes.
So you have to mention what's the column to plot, because first is t and another is dt by dx.
Sorry.
So
I'm not understanding you. Hello.
okay, I will message you.
Yeah. Okay. So I'll just write here red. Yeah, here. This. So if we plot this, so we can see temperature versus length. So we can see that at x is equal to 0, it is 300, and x is equal to 10, it is 1000. Let me check if I have written it or not.
Sorry, it's my mistake. My mistake. I misunderstood. Okay, carry on, carry on.
Okay, see, it is fine, right? Okay, so this is the one way we try to solve the problem. Okay, let me save this problem. Mm, here. Okay, but let's try to write our this thing in simpler way, where we don't want to define this function here at the below. So what we can do, this is the same thing I'm showing, but in a different way. So instead of writing this part here, defining all these things here, what we can directly do, we can define everything on top. So first I need to, yeah, first I need to define my equation. So yes, my equation is equal to the way we write here. It was x comma y. So here also we need to define equation at the rate x comma y. And my first equation is y of 2. I need this column, yeah. And yes, and my second equation is minus h into t underscore infinity minus y of 1. And I'm just closing. There's nothing new here. It's just different way of representation. And let's say I'm writing boundary condition is equal to, it is in form of ya and yb. So ya comma yb, and let's say I'm writing ya of 1 minus 300 and yb of 1 minus 1000, and sorry, 1000. And what is given to us? H is equal to 0.05, and t underscore infinite is equal to 298. Okay, let's just only run this. I want to show something else. So here I will be writing equation, or you what you can do. Let's just write it in the same way, so we don't need to get confused. Okay, so if I run this, I don't need to print everything. Yeah, here. So see, we got the same solution. Okay, so instead of those who don't want to write down long functions at the end, so this is the simpler way. You can just write down everything in a line. Yeah. So, okay. So let's move ahead with the problem statement. What is told to us? it is told that determine the temperature profile along the length of the rod as a function of ambient air temperature in the range of 100 to 500 Kelvin. So I now need to run a loop where my H is fixed, but my temperature range, this T infinity, is varying. So what I will do, I will put a comment here, and I will do for T underscore infinite is equal to what is the range from 100 to 500. So 100 to 500. If I'm not giving anything here in between the interval length, it will automatically take one. So let's say I'm giving the interval length of 100, or let's say it's 50. 100 to 500 in the range of 50. So let's see if I write it here, 100, 50, 500. So what it will do, it will go from 100 to 500 in the step of 50. So see 100, 150, 200. So it will go like this, and we need to put one end. Okay. So every time we want to plot it, so here we will have to put one hold on, because for each value of t, we need to show the plot. So if I run this, it should show me multiple plots. Okay, let me change the color criteria because everything it will show in red. So let it automatically choose the color. Okay, so see, this is how temperature profile along the length along the rod is varying with the variation in ambient temperature. Here also we can give the legends, but for this MATLAB part, if we are giving legend here, it will be very clumsy. So I have not given legend. So we can see that at 100, 200. So see, as our temperature is uh, going towards higher range, the it's not exactly straight line, but this curvature is significantly reducing. But the one thing is, it is starting with 300 and it should uh, end with 1000. But as our ambient air temperature is increasing, our convection is also increasing. So temperature it is achieving of, I should not say faster, but temperature difference it is achieving earlier. So see here at x is equal to 1, the temperature is near to 300 Kelvin only when my ambient air temperature is 100, but this at same point it is more than, near to, not near to 400, but more than 350. So that is the only difference that we are getting. So this was the part one of how we can see this with length of, with varying the temperature range. Now the second part is determine the temperature profile along the length of the rod as a function of heat transfer coefficient in the range of 0.01 to 10. So now we are supposed to vary heat transfer coefficient. So we will do the same thing. Now our T infinity is fixed. Our H is not fixed. So I will write down, I will modify my for loop. So for H is equal to, what is the limit? 0.01 to 10. So 0.01 to 10. Let's say I'm going in interval of 0.5. Okay. Everything else is same because we are not changing anything. We are just playing with variables. So if I run this, I can't see the plot. Yeah. So this is how it is varying. Let's take some wide range. Point, what I have taken, 0.01 to, let's say in interval of 0.01. So it will be a bit slow. It will take some time to show up the results. Taken so many points. See, here at this point, it is exactly straight line, and these are the various points. So this is how we can see the effect of both heat transfer coefficient as well as ambient air temperature. I hope this problem is clear. So what we can do now, okay, let me save this part. Okay. So I will just save this problem. This is our fifth problem of today's class. Example 5_2. Okay. So from this problem, what did we learn? We learned how temperature profile, how temperature varies when there is conduction plus convection for a cylindrical rod, or not cylindrical, just a rod of length L. We can see how temperature profile varies along the length of the rod when we are seeing the effect of both conduction and convection, and we are varying both the convection heat transfer coefficient H and ambient room temperature T infinite. So this is the problem, and from here what did we learn? We learned how to use bvp4c command. If we go for bvp5c, I guess for as we are taking so many points in between, so it will not affect. Sorry, where did I need to do bvp5c here? So as our is a fifth order method more accurate, but as our this this interval is good enough, so it will not affect our accuracy. So this was the one problem statement that we solved. So let's move ahead with one more problem statement. I don't know if this problem statement is solved by sir or not. The problem statement is: consider a one-dimensional catalyst pore in which a reaction takes place. The governing equation can be derived as the one given below. D squared Ca by dx square is equal to K divided by dAb into Ca, where Ca is the concentration of the reactant in kilomoles per meter cube. X is the distance variable in meter. K is the reaction rate constant in second inverse, means it's a first order reaction. And dAb is the diffusion constant meter square per second. The boundary conditions are given as Ca is equal to 1 at x is equal to 0, and dCa by dx is equal to 0 at x is equal to L. So the first part is given, K is equal to 2 into 10 raised to minus 3 second inverse, and dAb is given as 2.3 into 10 raised to minus 9 meter square per second. So the question is, for a pore length of 1 mm, determine the effect of rate constant and diffusion constant on the concentration. So first what we will do, for this 1 mm length and for the value of K and dAb, we will solve the problem, and then we will see the effect of both rate constant and diffusion constant. So we will keep one value of K fixed, and we will vary dAb, and then we will fix dAb, and we will vary then we will vary the value of K. Okay. What's your name? Excuse me. Hello.
My name is Raj Sundar. Raj Sundar.
Would you like to solve this problem?
Yeah, yeah. No, what should we use? Like PDEP. Oh, sorry. So
No, this
ODE
is
for like
boundary value. No, this is boundary
oh,
value
BBP4,
problem. So,
BBP4C, BBP4C.
so would you like to share your screen and do it if you are
No, I'm
fine
not.
with it?
I'm not good. I'm not good at MATLAB, so it will take too much time. So don't.
Okay,
It will
so
take.
I will write it down. I will write down the code and let me know if you are not understanding something. Okay.
Okay, sir.
Okay, so let me write down clear all CLC. So let's write down the first equation. Our equation is uh, d square Ca by dx square. So I will write Ca prime, Ca double prime plus here Ca double prime plus K into Ca by dAb, not plus, is equal to K into Ca divided by diffusivity. Okay. And boundary conditions are given as Ca of, in center it should be maximum. So Ca at x is equal to 0 is 1. Ca at x is equal to 0 is 1. And the second condition is dCA by, there is something different from what we have learned till the problem for today's problem equal to
Newman boundary condition.
0. Yes. So till now what we have, looked, if we see the previous problem statement, okay, let me close this one. Okay, so see here also it was y of 0 is equal to 0, y of pi by 2 is equal to 2, y of 1 divided by 3 pi is equal to 0, y of 1 is equal to something. Here also y of 0 is equal to 0, y of 1 is equal to 1. Same, but here the condition is different, that y of 0 is equal to 1 and the second boundary condition is derivative dCA by dx is equal to 0 and x is equal to 1. So it will be bit different. So let's try to solve it. Let's first define our mesh size. X mesh is equal to, so our one is center, that is x is equal to 0 and outer part x is equal to 1. So let's say I'm using linspace command. I hope you know how to use linspace. If not, tell me, I will
I know.
explain. 0, 1, comma. Let's say I'm taking some 10 points. We can change this. So I have defined my mesh size, X mesh. Now, my second part is what do I need to define? I need to use bvp init function to form this initial guess for boundary value problem solver. So I'm using bvp init. So for that, I need to define x comma y. So my x is x mesh and my y is y. I can give some random values. So let's say I'm giving some 1 comma 0. Okay, so this is my sol comma init. Okay, so let's do one thing here. Let's first define our equation. So that is what I have written the name. I just want to be consistent. ODE function. Okay, so my equation is ODE function is equal to at the rate, instead of writing my function at below, I'm writing the equation here. My equation is okay, I need to use this square brackets. So it is C of 2 and K into C of 1 divided by D. C of 2 means D square CA by DX square and CA is my C of 1. So this is my ODE function. What do I need to do now? I need to define my boundary condition. So my boundary function will be equal to at the rate of ya comma yb. Okay, what is my first boundary condition? Ca at x is equal to 0 is 1. So I will be writing ya of 1
1.
minus 1 is equal to 0. Correct? Ca at x is equal to 0 minus 1 is equal to 0. So that Ca at x is equal to 0 minus 1 is equal to 0. And my second boundary condition here, what we are given, dCA by dx we are
Yb of
given. So here instead of taking yb of 1, till now what we have taken yb of 1, but for this problem as it's dCA by dx, so we need to take yb of 2. Yb of 2 minus 0 is equal to 0. So I will just write yb of 2. Okay, let's do one thing. Let me write CACB because we are mentioning everywhere. Okay, let me write down in terms of y. It will be more convenient. Okay, YB. YB. Okay, so we have defined our ordinary this equation and we have defined boundary conditions. So now what do I need to do? I need to apply my solver. So that is solution is equal to BVP 4C, that is to solve boundary value problem using fourth order method VP4C. Now what is my equation? That is in ODE function part. What is my boundary condition? It is in this part BC function part, and remaining part for this BVP init X mesh and 1 comma 0. So that is in sol init. Okay, so we have created the solution. Now to plot it, I need to differentiate I need to separate out from solve. So if I open the previous question, so this x solve dot x will give me the value of x, and y will be given by solve dot y, first row all columns. And if we plot this, so on x-axis it is x, on y-axis it is y. Let's say I am just keeping some. Okay, let's not define anything here. Let's say I'm giving my line width is equal to 1.5. My x-axis is nothing but concentration. Sorry, x-axis is nothing but my length, pore length in meter. Let's say pore length, the unit is meter. We have forgotten one thing to define, that I will show you. And my y label is concentration. And what is the unit of concentration given in the question? The concentration is in units of kilomoles per meter cube. Okay, so the unit is here kilomole per meter cube. Okay, so one thing that we have not defined here is this part. We have not defined what is the value of K and what is the value of D. So let's define K is equal to what is the value of K? 2 into 10 is to minus 3. So I will write 2e minus 3. So it will give me 2 into 10 is to minus 3 second inverse. And what is the value of diffusivity? Diffusivity is given as 2.3 into 10 is to minus 9. So I will write 2.3 e minus 9. Okay. So let's see how it is varying. What should happen at x is equal to, it should reduce like this. We have made some mistake. Okay, we have written. Wait a minute. We have made some mistake. My boundary condition is ya of 1 minus 1, correct? And my second boundary condition is y of 2. Let me write down here. Zero to 1. Yeah, okay. The issue is here. We need to give from 1 to 0 because my first boundary is x is equal to 1 and second boundary is x is equal to 0. So I need to go from 1 to 0. Yes, it should not matter actually. Should not matter. I don't know what is the issue. X comma y. Our equation k is correct. 2 into 10 is to minus 3. 2 into 10 is to minus 3, right? Yeah. And d is 2.3 into 10 is to minus 9. Mass I have created from. Wait, let me just check this part.
0 to 1 will be fine.
Sorry?
0 to 1 will be fine. No, we are solving for 1 millimeter.
Yeah, it is
0 to
1
1
millimeter.
millimeter.
Yeah, it is 1 millimeter. So it is 0.001. Yeah. Thank you. 0.001. Yeah. It is the issue. Thank you. Yeah, okay. The point is I need to define from 0.0001 to 0, I guess, because my first boundary condition is defined as x is equal to 1. Sorry, yeah. My first boundary condition is defined as x is equal to 1 mm, and my second. Yeah, it's correct. It's correct. I'm sorry. Yeah, it should be 0, 0.001. Yeah. It is 0, x is equal to 0, it's defined, and x is equal to 1 mm, it's defined now. So it's correct. Okay. I guess it's not gonna affect anything. Yeah. This is how a solution will look like. If you can see at x is equal to 0, my CA is equal to 1 and my x is equal to 1, that dCA by dx is equal to 0. So my CA is some constant value. So this is how it should look like. When I took the reverse part, what did I initially do? I took this thing. So what it take here mathematically, it took that my x is equal to 1 meter, my this y is equal to 1. What did it took at x is equal to 1, CA is equal to 1, and x is equal to 0, it took dCA by dx is equal to 0. That's why we are getting inverse curve. But our correct condition is, first as x is equal to 0, it is this condition. Y of 1 is equal to 1 and my x is equal to 1 mm 0.001, it's this condition. Okay, so we should get this kind of plot where concentration is gradually reducing with pore length. Okay, is this clear? Okay, so let's do one thing. What is told to us, determine the effect of rate constant and diffusion constant on the concentration of reactant midway the pore length. Okay, so let's do one thing like the previous problem we did. Let's first keep d is equal to this value only, 2.3 into 10 raised to minus 9, and let's try to vary the value of k. Okay, so let's keep one for loop here. Yeah, here for k is equal to, what is the value of k? 2 into 10 raised to minus 3. Okay, we are not told anything about the range, so let's take some random range of 0.001 to 1. 0.001 to 0.1, let's say in gap of 0.01. I'm just experimenting it with value of k. I need to put one hold on command here because each with every for loop I should not get different curves. I should get all curves in at one place. So that's why in for loop only we need to put one hold on command before plotting. So if I plot it, so see we are seeing the effect, but this is really messy. So what we can do, 0.01, let me go from 0.1 to 0.5, some 10. Let's do this. Okay, 0, 1, 10. Yeah.
Yeah, you
So
have to try
what's,
very small value. You have to try very small
yeah,
value because
yeah,
the
but I want to show something here. Okay, so when it was my value was k is equal to 0.00, what was that value? 0.002, we were getting curve like this, correct? The curve was like this. But as I increase my rate constant from 1 to 10 range, what is happening? It is after some point two value of pore length, it is becoming constant. So what can you conclude from here?
the reaction
Can
has
you?
dominated the reaction dominated the process. I know the
Yeah,
reducing.
reaction is dominating. So what is happening? Reaction is occurring. So it is converting it. So within some pore length only, we are getting this value. So this what was I was willing to show. So I kept increased value. So this is one part. So let's do one thing. Now let's fix the value of k to this point and let's try to change the value of diffusivity. So let's say my diffusivity is varying from, I don't know how many variations we will be able to do for diffusivity, but I have tried from, uh, let's do 2 into 10 raised to minus 9, 2 into 10 raised to minus 9 to 5 into 10 raised to minus 9 -9. Okay. With let's say I'm increasing in range of 0.5 into 10 raised to -9. Okay. Everything else x k I have kept. Okay. So okay, let's try to put this. So see what's happening. Diffusion is really diffusivity first. Diffusion coefficient was 2 into 10 raised to -9. I guess it starts always starts with blue. So it is 2 into 10 raised to -9. Then as my diffusivity is going from 2 into 10 raised to -9 to 5 into 10 raised to -9, what's happening? Diffusivity is increasing, correct? So this
So
is
concentration
becoming,
increases.
yes. So it is
Concentration at a
becoming,
specific position.
yes, correct. So here there is one more curvature here, but here the curvature is less. So here we can also see the effect of diffusivity. So what we did, okay, with pore length. Okay, so this is what we done. We see the effect of both diffusivity and rate constant on this particular problem. So let me just save this problem. Is this problem taught by sir or not? I don't know. I'm just asking.
Ah, yes, yes. It is just taught by in the ninth week to the seventh lab,
Okay, I'm just taking these problems
but it's
for our
a
entire.
PDE problem, the
Okay,
partial
this was
differential
solved.
equation problem.
Okay, this was solved as PD problem. PD I will teach next week, not today. But this is as boundary condition problem I have shown. This problem was given to us in IT Kharagpur to solve using this BVP init. So I thought
Oh,
I should show you.
so you are a
And I guess,
SAS student.
sorry.
You are, Deshpande SAS student. You like it.
Yes, yes, I am a student.
Good.
He taught everything. This thing is us in IT
Ah,
Kharagpur. But there, what was that? It was not a whole course. It was half semester course for MATLAB and half semester course for COMSOL. So these are
oh,
everything it was
COMSOL.
taught to.
Oh, COMSOL. I know. I'm studying at electrochemical engineering in Central Electrochemical Research Institute. So we use a lot
Oh,
COMSOL.
great. Yeah, it must be useful.
So
Yeah.
I should do a course on COMSOL too then.
So yeah, I was taught the same course by him only at 2 years
Hmm.
ago, I guess. 2021. I guess in 2021. Okay. So this is what we learned in so I will wrap up the boundary value problems right now. So what we learned in today's class for boundary value problem, we learned some simple problems and we see how to solve this boundary value problem. So to solve any kind of boundary value problem, first we need to define the x mesh, so the size of the x that we are willing to take. Then we need to define we need to define using bvp init our x mass and our initial concentration or initial gas part using this bvp init, and we need to use this bvp init to solve this equation. So for that we need to use bvp 4c or bvp 5c, fourth order or fifth order method, where we need ODE function, boundary condition function, and this part, BVP init part. So to define ODE function, here I have written one separate function, dy by dx is equal to ODE function, and here I have written one separate function for boundary conditions. So for all these problems, the only difference was here that in the last problem of this reaction occurring in catalyst pore, we took the boundary condition. The second one was dCA by dx is equal to 0. So you need to be careful here that it should be yb of 2. What happened actually when I was solving this problem of this temperature variation along length? So what I did here, I by mistake took yb of 2 is equal to 1000. So what happened when I took yb of 2 is equal to 1000? Ideally, what should happen if this is my boundary condition? I'm just
Uh,
sharing these mistakes so you can be careful. So
okay,
this is
okay.
my boundary condition that x is equal to 0, temperature is 300 and x is equal to 10, temperature is 1000. So what I did, I by mistake take here yb of 2 is equal to 1000. So what was happening? It was not following the it was not showing me the exact solution. So see here, at one end, another end was not showing me the correct part. So it is showing some 4,500. So this is absolutely wrong. So be careful while you are writing it. YB of one, if it's a if the condition is given in dc by dx form, then only it should be YB2 or whatever in bracket 2. Okay. So this is what we learned. Okay, let me save this problem. Okay, I have not saved this. So this is our problem number example 6. Okay. Example 6. Okay. So now let's move ahead with partial differential equations. So in today's class, we are only running out of time. We have only 15 minutes left. So what I will do, I will take some questions from previous year's assignment where there are some simple one-liner questions for partial differential equation. So I will just give you some basis of partial differential equation through these questions. Okay. So the first question is choose the correct option to complete the string. Okay. Okay. Before doing all this nonsense, let me show you this part first. Um, techniques. This one. Yeah, here. This one. So what is partial differential equation? Can you tell me what is partial differential equation?
There are more than one independent variable.
More than
So
one
the dependent one
independent.
independent variable.
So let's say I am writing that d square t. Wait, let me zoom this. Yeah, let's say I'm writing that d square t. I'm sorry. Okay. Let's say I'm writing that d square t by dx square is equal to constant. So what kind of equation is this? Is this ordinary differential equation or partial
OD.
differential equation?
OD. It's
Okay.
OD.
This is an OD. Let's say I'm writing del t by del t is equal to del square t by del x square. So here there is one
It's
variable temperature, but here temperature is varying with both length
time and
as well as time. Yes. Yes, please say.
yes, it's varying with x and t.
X and t. So that's
Uh,
why this is called partial differential equation when we are having this one variable, one dependent variable and more than one independent variable. Okay, let me write down one more equation. Let me write down Laplace equation. So d square t by dx square but plus del square t by del y square is equal to 0. So this is steady state because there is no del t by del t term that is equal to 0. So this is steady state. But what is happening? Temperature is varying with both. Temperature
x
is
and
varying with
y.
both x as well as y. So this is called partial differential equation. So the first question is choose the correct option to complete the statement. A partial differential equation uh, contains one dependent and one independent and many independent and one dependent variable. Which one is correct?
C. The third option.
Option C is correct, where we are having
Option C.
many independent variables like x, comma y, comma z, comma time, and
These are
one dependent variable. Let's say it's temperature. Okay.
okay.
Okay, let's move ahead with the next problem. Okay, consider the following partial differential equation for heat conduction given by Fourier. Del T by del T is equal to alpha del square T by del x square plus del square T by del y square plus del square T by del z square, where alpha is thermal diffusivity. How alpha is defined? Alpha is equal to, if you know,
Uh, I know. But it's a K by rho CP.
rho into Cp. Yes, this is how thermal diffusivity is defined. Alpha is the thermal diffusivity and T is the temperature. So equation describes, does this describes unsteady state, steady state, transient or equilibrium.
I
So
don't
this
know
is
the
no
difference
way.
between unsteady state
Yes,
and transient. I don't know the difference.
yes.
What's the
So wait,
difference between unsteady state and transient?
yes. It's not steady state because it's this term. This is not equilibrium. Okay, so this is both this term, unsteady state as well as transient equation. Transient we can't exactly say, but unsteady state we can surely say. What is transient heat conduction equation? Transient we generally say when there is some heat generation term is involved. Wait, let me. I have written it down. Sorry, where did it go?
So,
Yeah, here.
so that's like the advective effects.
Sorry.
So the transient term is like that is a source or sink term.
Yes, exactly. So see, it's similar to that what I am saying, some heat, those kind of terms. Many tabs are open. Wait, transient heat conduction. Yeah, it is only function of time.
Oh,
No,
it's
no,
a
no,
only
sorry.
function of
No, 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 no. It can't be.
time.
That comes in lumped heat capacity analysis. Yeah, this is called transient heat conduction. You remember there is one, let's say I'm having one rod and wait, let me open that theory. I have written it down in my notes. Yeah, I can show you this part. It's called in lumped heat capacity part. It's there. Transient heat conduction. This term. Yeah, here. This thing, yeah. On steady state or transient heat conduction. So this is the term when we consider a small metal of volume V, density rho, and specific heat C at some temperature, and we suddenly immerse it in some large quantity of fluid at some T infinite temperature. So what is happening? Thermal conductivity of metal is very, very high. So what we assume that there is no temperature gradient inside the rod. So it only governs, there is no temperature gradient within the metal.
The temperature of the object will
Sorry?
decrease or increase. The temperature of the object will increase or decrease according to the T infinity.
Yes, yes. So here there is temperature is varying with time, this term. So if you perform mass balance minus mCp dt, that is equal to HAT minus T infinity into dt. So that varies with time. So this is transient. It's varying with time.
Okay.
I guess this is learned. I don't know if you have learned this or not.
No, we don't. We didn't have a heat transfer. We don't. We only have heat transfer one, and it contains only steady state operations only. We didn't
Okay.
even go to unsteady state.
Okay. So correct answer should be unsteady state only. Then next move ahead with next problem. Okay. So we have to match the following elliptic, parabolic. Okay, do you know what is elliptic partial differential equation,
I
parabolic and
know. I know.
hyperbolic?
I know. I know.
Okay,
I know.
can you
I know.
tell? Can you
So
tell?
elliptic is. Can you go back to the question?
No, not looking at question. What is the theory?
Oh,
How, when do you say
elliptic.
one?
Elliptic. So the time dependent term, which is dt by, let's say, dt by dt, d capital T by dt, is
Yes.
equal to so parabolic is d square t divided by dx
No, no,
square.
no. Those are shortcuts to understand, but that is not actual
Oh,
definition. These are shortcuts. Okay, I will show you. Okay, I also used
okay,
to
okay.
remember it like that only because it's not feasible to every time
That's no
calculate
problem.
eigenvalues. Okay, so I will show you. Okay, I closed that part. So okay, so what is called parabolic, elliptic, and hyperbolic? So when we write down our differential equation, Yeah. So we form this matrix of A11, A12, A13, A21, A22, A23, 31, 32, 33. So what is A11? A11 is coefficient of del square U by del X1 square. So let's say I'm having three variables. I won't be able to write down here. So let me open one blank, so I'll write.
The first one
Get.
is
Sorry?
elliptic equation. The
Yes.
second one is wave equation. You
First
could
one is
say, but I
elliptic.
don't know the second one
Yeah,
is wave.
okay. No, that is correct. That is easy to
I don't know
actually
the
remember. Okay. So let's say you are having U and U is varying with both x1, x2 and x3. So what kind of terms you can have? You can have del square U by del x1 square, del square U by del x1, del x2, or better if you write del x1, del x1, del square U by del x1, del x3. This is my
X3.
first row. Similarly,
Even
del square U by del x2, del x1, del
X1.
square U by del x2, del x2. So this is nothing but del square U by del x2 square and del square U by del x2, del x3. Like this, we form the matrix. So if there are three variables, so it will be del square U by del x3, x1, x3, x2, and del square U by del x3 square. I guess I have told it correctly. Let me
Okay,
just
okay.
cross check it. Yeah. Del square U by del x1 square, del square U by del x1, del x2, del x1. Like this, we form a matrix A of coefficient matrix where A11 is coefficient of del square U by del x1 square. A12 is coefficient of del square U by del x1, del x2. This term we generally don't have in our examples. So these terms A12, A13, A21, A23, these terms are generally zero. We only deal with this diagonal. So
Simple diagonal.
what is elliptic PD? If we find the eigenvalue of this matrix A, and if all eigenvalues are coming positive or all are negative, what does this mean? Meaning eigenvalues are of same sign. Let's say I'm getting 2 and 3. So those 2 and 3 are of same sign. So that is called elliptic PD. Let's say if I am getting eigenvalues as -1, -2. So both are as of same sign. So that is called elliptic PD. What is hyperbolic PD? We are getting mixture of positive and negative. So I am getting some 1, -1. So that is called hyperbolic PD. And let's say if I am getting at least one zero in my eigenvalue. So that is called parabolic PD. Okay.
Okay,
So
and the
if you see,
same sign
if,
elliptic, mixed sign
yeah, same
hyperbolic, at least 1 0 parabolic.
parabolic. So let's say this is the equation del square u by del x square plus del square u by del y square plus del square u by del z square is equal to 0. So my coefficient of this one is 1. There is no del x, del y, del x, del z term, right? So all these other terms will be 0, side terms will be 0, and on diagonal we will have 1. Correct?
It's
Correct?
simple. Property of
So
eigenvalues.
if I find the eigenvalue of this, it is coming all three eigenvalues as 1, 1, 1. So it is called elliptic PD. So our question is del square u by del square t by del square square plus del square t by del y square. So this will have same eigenvalues, like it's the similar
Over.
problem. So 1 comma 1 we will get. So it is a elliptic PD. So first one is elliptic PD. Okay. If we sorry, this one. So see this example. Del u by del t is equal to del square u by del x square plus del square u by del y square. Okay. So del square u by del x square term is having one coefficient of 1. This del square u by del y square is having one coefficient of 1. But this del u by del t, there is no term where we can define this. We have del 2 u by del x square kind of term, not del u by del x kind of term. So this coefficient will be
Homogeneous
for
equation.
t, it will be 0. So for this kind of equation, there is one, at least one 0. So this is called parabolic. So whenever you are having equation of del u by del t, it will always be parabolic. So that's how you remember it. And this kind of equation where it is del square u by del t square. So see, we have now three variables x comma y comma t. But what is that? Del square u by del t square is equal to del square u by del x square plus del square u by del y square. So my this coefficient is 1, 1, and this one coefficient is -1. So we are getting mixture of positive and negative eigenvalues. So this is called hyperbolic PD. So here, if you see the this example, this del square t by del x square is equal to something into del square y by del x square, and this will be positive only, right? This coefficient, because it is some x square, not x square, but something square. So that will be always a positive number. So this will be 1 and 1 coefficient is 1 and 1 coefficient will be -1 if we write it like this. So that's why it will be a hyperbolic PD. We will always get one negative eigenvalue, one positive and one negative. So it is hyperbolic. Okay.
Okay, okay. I
Did you
understood.
understand?
Thank you. Thank
Yeah,
you. I
the
understand. I
way
understand. This is
the thing that you said, it is actually easy to remember. You should remember it like this only, because every time you are not going to calculate eigenvalues.
eigenvalues. But I don't know the background theory on that. So it's good to hear the background theory too.
Yes.
So that's it.
Okay. Do you want to take snapshot something, or is it fine?
No, the lecture material will be available in no. They will be uploaded right to the website.
Which lecture material?
So this
This
lecture
one?
material you
No, I am
not
just
this one.
uploading.
That the problem one. This. No, the problem one. The
Yes,
exercises.
yes. This I will be uploading. Yeah.
So that will be enough.
Okay. So let's take a break for today. Let's meet next week. So from next week, we will see how to solve PD, and we will see more basic of these PD questions. We will write a code. How can we solve PD using this PDP MATLAB inbuilt function? Okay, so in today's lecture, what we learned boundary value problems. We solved boundary value problems using BVP4C and BVP5C MATLAB inbuilt function. And after that, we started looking at partial differential equation. We learned various kinds of PDs like elliptic, hyperbolic, and parabolic. So this is all for today's class. This part will be useful for next week. So thank you for joining. And if you
Thank
are having any query, please feel free to write me on this email ID.
you. Oh,
Okay. I hope you will join next week. So we'll meet next
I
week.
will. I will. I will.
Thank you.
Thank you. It's great of you to just teach like one person.
Yeah, actually, I'm not teaching anyone. No one is joining because sir is giving really easy questions that you don't even need to watch sir's lecture to solve those problems. So I assume that's why no one is joining.
No, it's not. I think it's pretty hard for me. I get error for every step I take. Every modification I made to the code, I will get error.
But that's how you learn.
It's
That's
good.
how
It's
you
good. It's
learn.
good. So good night.
Thank you so much. Let's meet next week
Thank you.
and
Thank you.
take care till then. Bye bye.
Okay. Thank you.